Okay, so we have defined chromatic number, and we have seen some bounds on it. So one of the bounds we consider was that the chromatic number is at least the clique number of G, which was pretty straightforward statement. If G has subgraph where all four of them are parallel adjacent, all of them must get different color. No matter what happens outside, you need at least four color. So this was very simple lower bound. Natural question is, how good is this bound? But I mean, this is lower bound. I mean, if in ideal situation, if we can upper bound it by some function of clique number, it would be very good. But it turns out that it's not bounded by any function. Such f does not exist. So, in some sense, this is not so good bound that the difference between these two could be arbitrarily high. So let's prove this. So first we will consider some operation which was introduced by Michalski. So let's say you have a graph shape. We consider Michalski's construction with the way to produce a new graph G prime from this G in the following way. So let the vertices of G be V1 to Vn. We add a vertex W to this vertex of G and an independent set U, which consists of the vertices U1 to Un. And then what we do is, for each I, we make this new vertex Ui adjacent to all of the neighbors of Vi, and let W be adjacent to all of the vertices in U. So this is a construction that produces a new graph from on given old graph. For example, what do you get if you apply this to, say, cycle of length 5? V1, V2, V3, V4, V5. Then you put U1, U2, maybe throwing this in another way is better. U1, U2, U3, U4, U5. And W. And then what do? You add an edge between these two, because V1 has a neighbor V2, V5. So U1 is adjacent to those two. And this way. And make W adjacent to all U1, U2, U3, U4, U5. This is what you obtain from the this C5. You apply Michalski's construction. Okay, why do we care about this? This is the way to produce graph from another graph in a way that the chromatic number increased while the clique number does not increase. Moreover, you can even bound the clique number in as small as possible. So if G is a chromatic number, which is triangle-free graph, here free means that something is free means that it doesn't contain this. So it's a graph that doesn't contain triangle as a subgraph. Then the graph G prime produced from G by Michalski's construction is K plus 1 chromatic. Then triangle free. So why do we prove this theorem? If this theorem is true, then C5 has a chromatic number 3 and triangle free, which means that its omega is 2. Clique number is 2. And then you apply this to this Michalski construction, then what you get is chromatic number 4, but the clique number is still 2. So you repeat this, then you get a graph whose chromatic number is arbitrarily high as you want, while its clique number is still 2. So it shows that this gap can be arbitrary. No matter what function you take here, f of 2 is bounded number, and you can find the graph whose chromatic number is bigger than f of 2. So this is what we want to prove. So let's prove that this theorem holds. So we consider the vertices V1, V2, and V1, U2, and W as above. So take G. And we produce G prime as above. And if, so we first prove that this is triangle free graph. G prime is triangle free graph. If what? There is a triangle in G prime, then as G itself is triangle free, this G prime, this triangle must contain a vertex which is not Pi. But also, we can see that there is no triangle containing W. Once you have a W, no matter how you choose the other two vertices, there are no edges between them. So there are no triangle in W. So it must contain a vertex UI and two of its neighbors in PG. However, what do you know? This has two neighbors. But then these two neighbors have to be adjacent. So this means that the triangle must contain an H of G. These two neighbors are both in here, so that if this is triangle, that means there is H here, and that H must belong to G. But this H, together with Pi instead of UI, forms a triangle in G, which is a contradiction, as G is triangle free. So G prime is triangle free. Okay, so now we want to show that G prime is K plus 1 chromatic. So chromatic number of G prime is at most K plus 1 is easy. Why? Because we can color G by K color and duplicate let's say let the color UI by the same color with BI and color W with a new color. Then it's easy to check that this is the proper coloring so that it can be colored with K plus 1 color. In our proof, that its chromatic number is bigger than K. Here K is what? Chromatic number of G. Okay, suppose that this G prime has a K coloring, and let's say it is G. And then this K coloring, if I don't mention it, and if I say K coloring, it already means a coloring using the color 1 to K. 1, 2, 3, K. So, without rest of generality, we assume that the G of W is K. And what do we have? Then every vertex UI is the neighbor of W. So the vertices in U have colors from 1 to K minus 1. None of them is colored with K. So now what's our goal? We start from the assumption that the G prime has a K coloring G. We will show that the G has even K minus 1 coloring, which is a contradiction. Because we assume that G is K chromatic. It requires K color, but we will contradict it by finding a proper K minus 1 coloring of G. So what do we do? That A with all the vertices BI with color under G is K. Then what do we know? We want to say we change the colors of BI in A to obtain a proper K minus 1 coloring of G to obtain a contradiction. So what do we do? For each BI in A, we change the color of this BI to G of UI. You see what color was used on UI, and then you copy it to BI. Then what? What do you know? First, we know that if set A lies in one color class of G, it is independent set. So there are no edges where the both of them are in A, so we don't have to care the possible problem from here. So if this change, we only have to check it that for an edge, say BI and B prime in G, where this BI is in A and B prime is in not A. What do you know? we have to check that these two vertices get different color in this modified coloring. But what do you know? If this is a color, then by construction, P prime and UI is also in H of G prime, which yields that G of B prime is different from G of UI. Hence, our modified coloring, our modification does not violate any edge within G. So what? We now delete U and W and obtain a proper K-1 coloring of G or contradiction. This shows that in order to color G prime, you need at least K plus 1 color. So we have shown that the G prime is indeed K plus 1 chromatic. So you start from say on H, and then you do this operation, and you get the C5, and then you get the next graph, and every time your number of vertices become double and plus 1, double and plus 1. So you obtain, if you do this, say, K1 2 times, then you obtain a K chromatic triangle free graph on 3 times 2 to the K minus 2 minus 1 vertices. So, in other words, there exists an n vertex graph with this being n, triangle free graph, with chromatic number at least some constant times log n. We can write that as omega of log n. So when we say A is omega of B, if, okay, it's actually about function. F of the n is omega of Gn if there is some constant C such that the positive constant C such that this holds. And we say that it's big O of Gn if there exists again constant C prime such that this holds. I mean, for convenience, technically this constant is positive, and let's say you take the absolute value. So this is more accurate definition. Okay, anyway, so this was not directly related to the lecture. So we have shown this. There are triangle free graphs with arbitrarily large chromatic number. So what does it say is that it says that the chromatic number of G is not really a local parameter, but a global parameter. So you forbid certain local structure, but the that doesn't guarantee that the chromatic number is bounded. Chromatic number could be large. Indeed, later we will show that there exists a graph which has graph with Gauss and list C, and let me write it this way: high Gauss and high chromatic number. So what is Gauss? Gauss is length of a shortest cycle in G. Meaning that if you have a graph with high Gauss, or at least 100, that means whatever 100 vertices you take, you will see no triangle. That means graph with Gauss G means that any G minus 1 vertex subset induces a forest. It doesn't contain any cycle. That means any G minus 1 vertex subset induces a forest which has chromatic number 2. Chromatic number at most 2. So it's 2 colorable. So any local structure is 2 colorable in this graph, but it could have a high chromatic number. So it shows that Gauss is more of not really a local parameter, but more of a global parameter. I mean, chromatic number is more of a global parameter than local parameter. On the other hand, we can, Gauss alone or the clique number alone does not bound the chromatic number. But if you see it, if you have n as a parameter, then here it's some function of n. So we might try to think n, the number of vertices, also as a parameter. Then maybe we can see how the forbidding local structure affects the chromatic number. So we can actually prove this proposition. If G is a triangle free, and vertex graph, then its chromatic number is at most 2 square root of n. Equivalently, every triangle free K chromatic graph has at least K square over 4 vertices. So this is quite an improvement than this bound. So it shows that there is K chromatic triangle free graph on exponentially many vertices. But here we have a K chromatic triangle free graph. No, it's the other way around. So, but here we show that every triangle free graph having K chromatic number has at least its polynomial many vertices. So in some sense, this statement and this statement are showing two different directions, and then there are quite a large gap. So we know that there exists such graph with exponentially many vertices, and we know that such graph all must have at least polynomially many vertices. So there are very big gaps. And actually the truth is more close to this. So this is more close to the optimal one than the above exponential bound. So we let the K, f of K, be the smallest order of triangle-free K chromatic number. Then what does this say? This proposition says that the f of K is at least K squared over 4. And Erdős used something called probabilistic method. So you use some sort of probabilistic tool to solve this problem to show that this f of K is at most of constant times K squared log square K. And later this value, Kim proved that okay, so upper bound and lower bound, one of them, the upper bound was actually proved by Jung and Kim, and the lower bound was, wait, who was it? Actually, yeah, so two different groups to prove the lower bound and upper bound, so that this f of K is actually some constant times K squared log K, and another constant times K squared log K. Yeah, this was later proved by Jung and Kim in 1995. And maybe give me a moment. Yeah. Itai and Komros and Femority prove lower bound here, and then Jung and Kim proved the upper bound here. So that the correct order of magnitude was, proved here. This means that if you have a triangle-free n vertex graph, then the chromatic number is at most square root of n over log n, and there exists a graph whose chromatic number is like some constant times, at least some constant times square root of n over log n. Anyway, so that's about some fact. Then let's prove this proposition. And so, proof. What do you know? In a triangle-free graph, if you have a vertex and it's taking its neighborhood, then this is independent. If there is an edge here, then you get a triangle, but you are triangle-free. Okay, so, but what do we want to do? We want to color the graph. We have to find the proper color, which is same as partition of the vertex into independent. That means if you have a vertex with a large degree, then you take its neighbor, and then that's your independent set. You can keep one color to it, and then you just throw it away. Not throw it away, but you make it one part in your partition. So, as long as G has a vertex with at least square root of n neighbors, which is not yet colored, we use one color on those vertices, and but because she only have n vertices, we can do this at most square root of n times. Each time you color square root of n vertices, so you can do at most square root of n times. After this, what? The subgraph induced by the remaining vertices, remaining uncolored vertices, this, I mean, we don't know how many vertices it has, but we know it has maximum degree less than square root of n. Because it has a vertex with the degree at least square root of n, and we could have done this step one more time. Thus, what? Greedy coloring, as we did before, on this graph with the totally new set of color, produce the proper coloring of this subgraph using a most cute of an additional color. Hence, altogether, it's n mod 2 square root of n, and that's implies this. So, yeah, both of them. Okay, so we have explored the relationship between clique number and chromatic number. And in next video, we will consider a variation of this proper coloring, which is called the list coloring. Yeah, that's what we will talk about in next video. Okay, and see you in next video.